Okay.
Okay, let me figure out where to put this. So tell me if you can hear me all right. Yeah, sounds good. Okay, so this is going to be a little bit different than yesterday because now I'm actually here. And I guess that makes me easier to reach with questions. So if I'm starting to say things too fast, or if you want something explained, you can interrupt me easier. So and today, so I took a long detour. So I tried to explain a little bit about background, so a little bit about theory of modular forms. But really, I mean, what you all want to hear about is so how does it help with the proof of universal optimality? And well, in fact, it doesn't help with the proof of universal optimality directly, but it helps through an interpolation formula, which then turns out to give a magic function, which actually gives the precise bound for the Kohn-Kummer linear programming bound for energy. And I mean, there's an extra step which I will definitely not explain, which is so you come up with a candidate for the magic function using this interpolation formula that I will explain a little bit today and a little bit tomorrow. But there's an extra step where you actually have to verify some inequalities. And that step is a little bit disappointing because there's no conceptual explanation why everything works out in the end. It's just some fact of the universe that in these dimensions, everything works well. And unfortunately, I mean, we also want to solve another problem of similar type. And then if we understood better why everything works, maybe it would help. But so most of the like speculational and some maybe more interesting stuff will come tomorrow. So today I will slowly go from more classical theory of modular forms to the actual like the actual theory that's used in proving the interpolation form. Okay. So what I want to do is first I will start with what is the tool that we will use, and then I will explain why it actually is useful and how it's used in this Fourier interpolation business. So, and I want to remind you something that we discussed a couple of times already. So recall G2. So it was an Eisenstage series which wasn't modular. So not modular. But it's kind of interesting nonetheless, because so its transformation law was still quite simple. And I'll give it precisely, but for the rest of the talk, it won't really matter what this function on the right is. So let me just call it phi with index gamma tau, and as usual, gamma will be a matrix, a 2x2 matrix in PSL2Z. And well, here I also have to put the variable, but that's not too important. So what's special about this family of functions phi gamma? Well, there's one, so it's not a completely arbitrary family because there's one condition that they have to satisfy. So let me write it down first, and then I will explain. So for any two matrices, in PSL2Z, yes?
You can run the table if you use this.
Oh.
Then on the border of the table.
Oh, that's excellent. Amazing. Okay, this is much more convenient. Okay, so then, so there is a compatibility condition that these functions should satisfy, and actually, it's like a computation which is not completely trivial. In fact, to check that this function here, this does satisfy this property. So this. satisfies it. And the easiest way to do this exercise is actually to use this identity. So you can, of course, check it directly, but it's somehow a boring calculation. So let me explain where this condition comes from. So really, so phi gamma is the difference between, well, G2 and G2 acted on by gamma. Oh, there's something. Oh, is there a way to hide it? Yeah. Well, no, that's not what I wanted. It's not minimized. Okay, now this is good. Okay. Yes. So I just wanted to explain, well, where this condition comes from, and it's just like a, well, simple calculation. So you just look at what each term here is in terms of G2. And it's, you kind of see that there's some cancellation going on. Gamma 1 / gamma 2. So I'm eating this index too because it doesn't really play any role. And then you see that this term appears here and it appears here, so they actually cancel out. And then you're left with G2 minus G2 gamma 1 gamma 2. Oops. And this is what we called phi gamma 1 gamma 2. So this was phi gamma 2. And this is phi gamma 1 acted on by element gamma 2. So what this is, so what this means more conceptually, so this means that phi gamma, so the collection of all these functions is what is called the one cocycle in group cohomology, for the group gamma 1. And that's about as far as I will go into cohomology. So if you're not familiar with group cohomology, I won't really use any results from it, but just to give you some idea what it's related to. And so, well, this identity, there's several ways you can look at it, but at least one of them tells you that if you know, so if you know phi gamma or gamma in generators, then this allows you to reconstruct all the other values. For the group, and so I was talking about the group gamma 1, but in principle there's nothing special about it, so you can work with it in any case. And more, but however, there's like an abstraction to that. So the only problem, so if there are relations in between generators, then this family also has to respect them. So phi gamma. So the family of functions restricted to generators has some additional conditions as to respect them. And I won't go into detail exactly what this means, but roughly, so if you have I don't know, a relation of this type, then you can compute phi identity, which is always 0 in any cocycle, is equal to phi gamma 1 gamma n, and then you repeatedly apply this cocycle condition. So it's some combination of phi, well, some other gamma I tilde acted on by some other elements, gamma j tilde, well, double tilde. So I mean, one can actually write down, it's not completely random, but I don't want to do that. So it gives a lot of relations. But then I think, well, basically, so these types of conditions are the only abstractions to extending something from the generators to the full group. So this will actually be important, and it's kind of it's quite a subtle thing that actually you have to use some special groups to obtain this interpolation phenomenon I will be talking about. And the absence of relations is first of all, it's necessary, but also it's very restrictive. So somehow the theory doesn't generalize easily because of that. So, but this you can ignore for the moment. So I will come back to it when I actually need it. So let me just make this definition clear. So a collection of functions for any group, well, let's say for gamma 1, but we will specialize to other groups soon. So it's called, this collection is called a one cocycle if it satisfies this star condition I was talking about. And so what one can also do is we can also restrict, so we can consider phi gamma to be elements from some class of functions. So I don't know, P, some class of nice functions. For example, we can consider things which are polynomials, and this has some non-trivial applications in modular form theory. But the class, so I have a particular class P in mind, which is very important in what follows. So let's call P a class of functions. I'll use phi again on upper half plane. So holomorphic and of moderate growth. So and of moderate growth. So what this means, it means that the functions have to satisfy some growth condition in the upper half plane, and it's of the form, so we want it to be bounded by some negative power of imaginary part, plus maybe some power of absolute value. And so this may look like somewhat arbitrary restriction, but maybe for people doing functional analysis with spaces of analytic functions, there's a more, well, maybe cleaner way to rewrite this condition. So this condition here is equivalent to, so if we map the upper half plane conformally onto the unit disk, so this map does the inverse map from the unit disk to upper half plane. So the condition becomes somewhat, well, similar to the definition of Bergman spaces. So you want somehow some bound on how the function grows towards the boundary of the disk. So this is just an aside. Okay, so why do we restrict to this class? So I defined what a one cocycle is, but really the only reason I defined it is because I want to pose a problem. So problem, well, okay, so definition. What is a modular integral? So given a one cocycle by gamma, a modular integral for it. So is well, any function let's say, so we consider class in P, and any function f that we also want to be in P, such that, so we kind of the way we derived the condition for one cocycles was by looking at certain one cocycles of special type, and this is exactly what we want. So we want this to happen for all elements in the group. So in terms of like cohomology, this means that this one, so this condition, the existence of such a function just means that the cocycle is trivial in the cohomology group. But what's kind of a funny thing is that we actually don't care so much about well, like the cohomology, but about the preimage. So this the preimage under the coboundary map. So this, and so what we want to note, yeah, there's also the weight. So modular integral of weight k, and the cocycle is also of weight k. Okay, so and note, so if such a thing exists, so if f exists at all, then it's almost it's well defined up to a space of modular forms. So it is, in a certain sense, it's unique up to finite dimensional corrections. It is modulo, the space of modular forms for this group. So it's just something that you check directly from the definition. So if you take two such functions and the difference between two such functions for the same cocycle is a modular form. So in particular, if your space of modular forms is empty, then you get somehow a unique. So each cocycle, it defines at most one function, which is a modular integral.
Sorry, what's the tiny k then at the bottom?
Where?
Is it f minus f line k?
Yeah, so this was, so the, okay, so let's just recall, so f slash k gamma was this slash action operator in weight k.
Yeah.
So, I mean, at this level of discussion, it actually doesn't really matter because so everything I'm saying so far is completely group cohomological, so you can define it in much more general situation. So now I will talk about what happens for weight k cocycles. And so there is a result actually, which is reasonably old, which in a sense tells you that, well, it tells you quite a lot about modular cocycles as long as the weight is greater than 2 or greater than or equal to 2. So it's a theorem by Marvin Knopp in 1974, which tells you, so if the weight, and here it's now important that we're talking about modular forms, so not just about arbitrary abstract group cohomology. So if the weight is at least 2, then any cocycle well, I have to, any one cocycle phi gamma has a modular integral. So, so any phi gamma, any cocycle again in P has a modular integral in P. So in the space of moderately growing functions. Okay, so as you will see, this is actually a very strong result because so if you don't care about explicitly finding this modular integral, it almost immediately implies existence of Fourier interpolation formulas. So, and let's see, so when did I start? Did I start at 20 past, 25 past, right?
25.
Okay, no, I think I'm good. So I'll sketch a little bit about the proof. And it will illustrate, so the proof is direct, and in a sense it's constructive, but it's very hard to use it. And I'll explain why. So what you do is, so first of all, let me restate the construction of Eisenstage series. So Eisenstage series, so we defined it somehow like this. well, maybe GM. So it was a sum over some pairs CD, 1 over C tau plus D to the M. And it's, well, it's a nice definition, but there's, well, there was some normalization constant here. But if you use this group action notation, it's actually much cleaner to write it as follows. So it's the sum over all coset representatives, and I will explain what this gamma infinity is in a moment, of constant function 1 acted on in weight M by the element gamma. And so gamma infinity is just, well, the set of powers of the T matrix. So it's just a set of all upper triangular matrices with one some diagonal. I mean, it's just this thing. And gamma 1, it's as before, it's PSL to Z. Although, I mean, with this notation, it doesn't really matter which group it is. So it works quite generally. So, and the idea of NOP was similar. So what you do is you construct your, so you first construct a solution to a different problem, and I'll just write what the construction is. So you do the same sum of, but now over your set of cocycles, multiplied by 1 acted on in weight M. And so and M is something that you choose. So we have a number K. So K is the weight. And you choose an additional number M. And so you act, so this thing is of weight K. Yes?
It is just a kind of mismatch what I was expecting, because gamma is a matrix, but it's also a cocycle, or how does it work?
No. Phi with index gamma is the cocycle, is the
Yeah, but when you write the sum over gamma infinity over gamma 1 of 1 slash M gamma, then this doesn't depend on the.
Yeah, so the point, yeah, so the point is this actually doesn't depend on the choice of the representative, because gamma infinity acts on 1 identically. So that's and here it's also, well, that's the important part. And it also tells you that you have to do something like that, because otherwise you have 1 infinitely many times, so it will never converge. So there's like very short calculation that shows that it's almost a solution. And let me do it. Oops. So you look at how in weight K plus M, some other element gamma prime acts on this sum. And so I'll just do this calculation quickly. And I'll make a few comments. Gamma times gamma prime. So first, you just directly apply the slash operator to each term in the expression. And then, so you use the condition for the cocycle. And the condition for the cocycle tells you that this each term here you can rewrite as a difference of 2 values of phi, and then times the old thing. And okay. Sorry, I forgot a very important thing to say. So let's assume that phi t is 0. Yeah, maybe that was what led to confusion. So this thing is then well defined, so it doesn't depend on the choice of the coset representative. Yeah, so this is actually important, but there's a simple way of how to deal with this. So then this thing will go through. So the first summation, you just change. Here it has to be the set of cosets. So in the first summation, just change gamma prime to gamma. So it runs over the same set. So you get psi again. And in the second case, well, phi gamma prime is constant. I mean, it's the same for all terms of summations. So you just carry it out. And then the rest is, well, the sum of 1 slash M gamma, which we know it's an Eisenstage series. So you almost get what you want. So if you actually divide psi by em, this will be a modular cocycle, a modular integral for phi gamma. So there are two problems. Well, first was how to make this condition hold, and that's not really a big problem. So to force phi sub t equals 0, one just chooses some solution to a simpler problem. Oops. To f, well, maybe let's call this g minus g slash t is equal to phi t. So it's just some translation, like functional equation with respect to translation. So you can solve it in many different ways directly, or you can guess a solution, or you can write some infinite sum which does it. So that's usually easy, and then you subtract it off from your cocycle. So that reduces to this problem. But the bigger problem is this thing is meromorphic. So this thing is meromorphic, and that means you have to do another step, meromorphic in general. And then you have to correct, so you have to remove all the poles. So, and that leads to a mess. I mean, you can work it out, but it's very hard to prove some qualitative results about it. Okay, so, but roughly that is the sketch. And so now let's come to a more important question. So why do we actually care about these things? So why do we want to study these objects? Modular integrals, I mean. And so there are two reasons. So one is more of interest to the people doing modular form theory. So there is something called Eichler Shimura theory. And I will briefly explain what it is, but it's not of much importance for the rest of the talk. But let me just sketch what the theory is about. So let's say you have a cusp form for gamma 1. Then, well, there's an Eichler integral that you can associate to this cusp form. And it's a very simple thing, but it's maybe not immediately obvious why it's a good thing. So it's just the k minus first primitive of the function f. So it's k minus first primitive of f. But actually, well, there's several ways you can normalize it, but there's a particularly nice one which comes from Cauchy's iterated integral formula. So you just define it in this way. So it's the integral from tau to infinity of your function f of z times tau minus z to the power k minus 2 dz. And there, I mean, there's some constants you have to put in front so that it's actually a primitive, but that's not too important. So that's just how you define this Eichler integral. And the beautiful thing is that f is almost a modular form. So it's a modular integral for something, for a cocycle which is polynomial. And so f ends up, f is a modular integral. Well, with a polynomial cocycle. So I won't say much more about this story, but I want to say a few things. So first, so why this is good? Well, it turns out that one can study many things about the original cusp form f. So just by looking at a certain polynomial. And this is, so this is called the period polynomial. Of f. And so this polynomial has some nice transformation properties. And it turns out that almost everything that you can ask about the function f and many arithmetic properties of it, like how it behaves with respect to Hecke operators, which I haven't talked about, but this is this is of interest in arithmetic applications. So this you can compute just by looking at this polynomial. And it's much easier. So actually many ways of computing with modular forms actually don't work with forms themselves, but with these period polynomials. But let me just give you well, the reason why this whole story works is a completely elementary identity, which is actually, well, not very easy to prove if you don't know how to do that.
If large F is like in the previous part, is Eichler.
Large F is exactly this thing. Yes. It's this stuff. Yeah. Well, so there's an identity which is completely elementary, which is called Ball's identity. And so let me just do some normalization, though that's not too important. So it's just the differentiation with respect to tau, but normalized by 1/2 pi I. So there's an identity which holds for any smooth function on the upper half plane. So for any f smooth function, we have an identity that if you take action with respect to SL to Z in weight 2 minus k, and then differentiate k minus 1 times, that's the same as differentiating k minus 1 times first and then acting in weight k. And I mean, it might look innocent, but if you actually try to work it out directly, it's quite painful. So you start expanding these iterated derivatives, and it looks like it will nothing will cancel out. You'll get tons of terms. It will be a terrible mess. But in the end, actually, everything cancels out. You get this nice relation, and it only works if you do exactly k minus 1 times differentiation, and you act in these ways. So it's a very nice elementary identity, which implies this whole Eichler-Shimura theory, more or less. Okay, so that was maybe not so interesting for this audience, but okay, let me give you another reason why you should care. So the real reason for this course is Fourier interpolation, and it turns out that with this theory of modular integrals, in some cases it's a trivial corollary of Marvin Knopp's result. So let me now come back to the first lecture. So what I really want to explain is how this identity, how to prove this interpolation identity in dimension 8 and 24. But let me just formulate it in dimension 8. So yeah, I mean, it's not very interesting to rewrite it, but I guess I started it. Okay, so instead of proving this, so this, I will come back to this tomorrow, but let me prove a result which is very similar. So let's look, instead of dimension 8, let's look at radial functions in dimension 4, and let's prove the same formula, but without derivatives. So you have 2 times fewer functions. an hat x. So this result is tight. So this summation, it actually has to start with 1 on both sides. So what is the way to prove it? So you convert it into a question about modular integrals. And there's just one idea, which is very simple. So you forget about x. So just fix x and try to prove an identity for a fixed x. So this thing is linear. So this identity 1 is linear in F. And we want to prove it for all radial Schwartz functions. So if we pick a nice family of test functions which have dense span, then this will be enough. And this nice family is just the complex Gaussians.
Sorry, just to check, are we looking for a function f that satisfies that form?
So we want to prove there exists an of x. So let me do it such that for all f. So we want a universal reconstruction formula for radial functions in our form. That make more sense? Okay. So this identity that we want to prove, so we don't know that it's true for anything, but it's linear enough, so it's enough to prove it for a large collection of things. And it's an exercise, but not for this course, but like for course in, I guess, functional analysis, to prove that this actually does the job. So this collection of functions is dense. So it's dense in this space. Okay, so that I will not do, but now you just you rewrite what this means. So for this identity to hold for a family of Gaussians. So you just introduce some notation. So let's call it fx of tau.
So Danylo, can I ask
Yes.
something before you go into the details?
Yes.
So this looks kind of similar to Poisson summation, but it's not exactly Poisson summation. So what is the value added?
So Poisson summation is related to this formula. So it's kind of so if you included zeros, the Poisson summation will tell you what is the redundancy in the set of points you're using. So if you just send f to these two collections numbers, and so I'm still doing this kind of abuse of notation where I'm treating radial functions as one variable functions. So if you just think about this map, so what this tells you is that this map is injective, and Poisson summation formula gives you the co-kernel. And in fact, but the way I wrote it here, the map is also surjective on the space of rapidly decreasing sequences. So it's kind of a nice fact that well, I think it's quite well known. So the Schwartz space of functions is abstractly isomorphic to Schwartz space of sequences, and that you can prove in many different ways. But this kind of directly gives you that. So you just take specializations to a certain sequence, and you get this isomorphism directly. So this is where Poisson summation formulas come in. So it's kind of the redundancy between these values. But yeah, the way I wrote it, unfortunately, doesn't appear. But coming back to the proof, so this is an honest proof. So, but it will not give you the formulas. So so you start with just introducing some notation. And I mean, the whole thing is backwards because you don't know that any of this makes sense at this point in time. And but you just define these two things. And you note, well, that this is two periodic. And the other thing is also two periodic as a function of tau, just by construction. And so the only thing that they satisfy is this identity 1, and if you rewrite it, it means fx of tau minus tau to the minus 2 gx of minus 1 over tau is equal to e to the pi I tau x squared. So this is what you want. And well, the other thing is you don't want these sequences to grow too quickly. And that is where this condition, this P condition comes in. So you also want fx gx to be in this class P of moderately growing functions. But let me explain why this thing is actually a question about modular integrals, and it's very easy. So first, let's just ignore gx completely and look at what this identity tells you. So it tells you that fx minus fx slash t squared is 0. So this is the periodicity. And the other thing that now looking at this condition, so I don't know, double star. Oh yeah, this slash 2, yes. But here, so if you think about this condition, well, so if you now slash this thing with s t squared s and subtract it from the original thing, so this term will disappear. So what this tells you is fx minus fx slash s t squared s. So s t squared s is just this matrix. So this matrix stabilizes this expression here because gx is too periodic. It's equal to this thing minus, I mean, it has to be a dot and st squared s. And again, it's in weight 2. And so this almost looks like a modular integral property. And in fact, well, we just define, we extend, so a cocycle, so an extension from phi t square equals 0 and phi s t square s equals this thing here. So it's just some function, phi naught of tau. I mean, this not, well, maybe psi of tau. So, and the point is, so you had an exercise well, you had it yesterday that gamma 2 is free on these two generators. That means that you can make this extension work. So there is no kind of, at no point will you get contradictions. You can extend this thing to the full group. And because of that, so you get Knopf's result implies you that fx exists. So there is a solution in P. And then you can also define gx by just this formula. So this kind of proves everything. So it proves that there is a formula of this type, and it is unique. And it is in fact unique. So one is unique. And the uniqueness because the space of forms of modular forms, so this kind of the space modular which we well defined, it has dimension 2, and we kill these 2 degrees of freedom exactly by starting not from 0 here and here, but from 1. So this is where this uniqueness comes in. So this proves everything. Yeah, you could make a different choice to kill this freedom yeah. So yeah, in that sense, it's not canonical, but there's other things which make this a nice choice. So in a certain sense, this theorem follows very easily from Knopf's results. And the difficult part was to realize that this is a feasible approach. So this is yeah, this was a difficult thing, kind of to conceptualize what's going on and to realize.
Can I ask another question? Yeah, so as somebody who's definitely not in modular forms, so this identity 2 star, if I try to think sort of what it reminded me of. So one thing that might remind me of is the Jacobi identity for the theta function or something like that.
Yeah.
So is there a connection to that?
Well, I mean, so it's kind of a non.
In the Jacobi identity, you would have that the F is equal to the G.
Yeah.
And,
So you would have 0 here.
and,
Right?
and you have a 0 here.
Yeah.
So it's some funny deformation of
Yeah,
the Jacobi
yeah,
identity.
yeah.
So is there any? I mean, can you help me understand it from this viewpoint?
From this viewpoint. So, well, I mean, maybe, so you think about this maybe as like a series of ordinary differential equations, and then the theta series is like a homogeneous.
I think of it as a solution to a functional
Yeah,
equation.
yeah.
Basically. That's what
So it's kind of going between solutions to homogeneous functional equations to non-homogeneous functional equations. And there is kind of a way to interpret it in this way. But there's a lot of, well, so let me see how I'm doing on time. I have 5 more minutes.
Because the theta function would be a special case of a modular form, right?
Yes, yes,
So
yes.
but it's a simpler one than the ones here.
Yeah, yeah. So like yeah, this theory is kind of strange.
Special choice of X.
For a special choice of X. So if you take X to be 0, then you recover the Poisson summation formula actually.
But I want to get 0, not 1. I mean, I want to get 0 on the right hand side to get Jacobi identity. And when you take X equals 0, you get 1. So it's not
I mean, it is directly related, but so if you think about theta of tau and you split off the constant term plus another function, then you would get, for this function you would have a non-zero thing on the right hand side. But I mean, it's so the modular forms kind of come in, but they're like the error in what you're trying to solve, like the space up to which you're well defined. So I don't know. Yeah, but this whole story is very much tied to this fact. So this is absolutely crucial. This freeness, and the big problem with the whole approach is that this is extremely rare. So, well, it's not extremely rare to have free groups, but they usually have tons of generators, and then you can't tie it to something like Fourier analytics simply. And this so it's almost never this method of proving this the Fourier interpolation formula is very hard to generalize. And tomorrow I will tell some conjectures and some more general framework that we're trying to develop that kind of, so most of that is conjectural because we don't have a way of kind of eliminating the nice modular form theoretic techniques. We don't have anything to replace them with. But I will talk about that more tomorrow. And so, I don't know, I have 2 minutes, right? So the problem with this approach is that Knopf's result is not constructive. Well, it's constructive, but it's not very useful because it involves, yes? Oh. Yeah. Okay. So there's a better way to do this. So how to do this constructively? Find modular integrals. So how to? And we actually do need this for the universal optimality, because at some point we actually have to do something with these functions. We have to prove inequalities. And with Knopf's approach, you can prove existence for the 8-dimensional this interpolation formula I started with, for this one. So you can prove that there exists such a formula with Knopf's result, but it's not good enough to actually prove anything about the functions themselves. And that's why we have to do it differently. And so that I will explain it tomorrow. Okay. And yeah, so maybe let's leave it for tomorrow. And today, so Steven will talk a little bit more about this Eichler-Shimura theory that I kind of really very briefly sketched. So that thing has some interesting number theoretic implications.
Are there any questions? Before doesn't seem possible. Okay, so then let's take Danilo, and then we are moving to the Stevens part of the maybe 5 minutes break so that we can.